Sorry for the short delay in getting this started. It's a pleasure for me to present a discussion on the question of how Hydro-Québec has accepted the fact that climate change is taking place and that we have to find ways of adapting to it. I will first of all describe the Hydro-Québec power system and mention that Hydro-Québec has a very strong reliance on climate. And we'll take a look at the identification of problems that are being dealt with, impact assessment on hydrological conditions, impact assessment, the adaptation approaches, experimental methods, results, operational changes, non-structural, as well as modifications to structures, etc., and a combination of the two. I hope I can do a better presentation than manipulating this thing. Oh my God. Okay. Sorry. 97% of the electricity produced by Hydro-Québec comes from hydro sources. There's a very minor part coming from fossil fuels, and etc. 57 powerhouses, generating a total of 35,000 megawatts of energy. There are 26 reservoirs, total capacity of 175 terawatt hours. And renewable energy, of course, comes from precipitation, which is very, very strongly associated with climate. We see that in the far north, we have the Churchill Falls and the La Grande project, which constitutes about 60% of the productivity. The average annual production is about 175 terawatt hours, with 26 reservoirs, etc. Somebody should have told me how to use this thing because I'm not able to do it properly.
Let's see.
What's going on?
You should be okay with that one. So it's that one there.
Okay, fine. Extreme climate events have taken place in the last 10 or 20 years. There was been, first of all, the Saguenay flood in the Lake St. John region of northern Quebec, and there was $800 million worth of damage. A second event took place in 1998, which was an ice and rain event, and that resulted in $1.6 billion of damage. The inflow to a water-driven system is variable. We call annual energy inflow as the anticipated productivity of water flowing into the watersheds. And energy varies from 1 year to energy input varies from 1 year to another. And if we take a look at the period from 1943 to 1966, that first part on the left-hand side, we see that there was a kind of balance between the number of surplus years as compared with the number of deficit years relative to the mean annual value. And we get this critical sequence in 60 to 63, and many of the hydro projects have been designed and were strongly influenced by this passing event. We get the next period in which, from 1963 to 1985, in which basically there was a lot of surplus energy, and there was actually a rebound of reservoir conditions. The third period constitutes the period 1985 to 2005, in which again we fell into a strong period of deficits. So climate has a variability. What is the problem to be resolved? First of all, a hydroelectric system is composed of physical configuration, dams, powerhouses, canals, etc. And each of these structures are operated in a specific way. Now, how do we decide how to operate them? Well, it all depends upon the hydrological conditions that are there, plus, of course, the demand and the economic considerations. But what is the hydrological regime dependent upon? Well, it depends upon the actual climate. So there's a relationship between physical operating rules, hydrology, and the climate itself. We all know the climate is changing. Oh, well, the climate's going to change. Well, then the hydrological conditions change. Well, if the hydrological conditions change, we have to do something about it. We have to either make some changes in the physical configuration or make some changes in the operating rules. So what is the real true question that we are dealing with? And that is how to manage climate change-associated impacts in water resources projects, the existing and planning. I'm speaking of hydroelectricity, but this entire presentation could be equally applied to irrigation, to domestic water supply, or other problems. So what do we have to do? We have to first of all say, well, what is the climate change impact identification? What's happening to climate change? What is the impact? What is the evolution of this impact? Is that the climate is not just changed now, today, and it's going to be that way for the next 50 or 100 years. It's dynamic. And what is the evolution of the various adaptation measures? We don't just decide today we're going to make a change that's going to be applied in 50 years. We have to have a progressive development of this. And we have to select appropriate adaptation measures which are compatible with the structures and the such like. So now let's take a look at some examples of an ongoing assessments where we had an application to the Hydro-Québec network where there was 94 watersheds, 90 different climate change projections, because there's uncertainty in with these projections. And we're looking for the projection of the future inflows. Remember back the slide where we said inflows had a strong impact. And we have to look at a multiple number of scenarios. Let's take a look at what the spatial variability anticipated for the horizon in the 2050 period. Well, first of all, without the entire watershed, the entire Quebec area, etc., it is found that all inflow changes will be positive. They are stronger in the far north with about 10 to 14% increase in the mean annual flow, and in the southern watersheds, maybe 1 to 8%. So we're getting a positive change. How are we going to be able to handle this? Well, we're very fortunate in the Hydro-Québec system because we have a very flexible system. It consists of many, many reservoirs, many power stations, different rivers, which incidentally, you notice from the slide, they have a different change in impact, so that we got a little bit of flexibility, which is going to be helping us out. Let's take a look at a typical evaluation of the annual hydrological regime. And here we see a situation, the black line is the actual conditions from 1961 to 2007, and these other colored lines are one of the 90 different climate change projections that have been evaluated. Well, what happens? We see that in the fall and the winter period, which this incident is January to December, in the fall and the winter period there, the inflows are significantly higher. Well, why? Well, this is due to the fact that historically in this area there was a lot of snowfall and snowfall and formation of ice, so there was accumulation of water. Well, with the climate change, that's no longer going to happen. It's going to be rain, 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 and as a result in this fall period, there's not going to be the accumulation of this mass of water in the lakes and in frozen. So we're getting larger flows in the wintertime. And we see this right through for the period January, February, March, etc. Significantly greater intensity of inflows, almost in some cases twice the historical value. The spring now comes about 2 to 4 weeks earlier than before. There's a little bit of impact on the peak values, but then again we're getting the summer period in which we get a lower thing. This is the key of the presentation, in my opinion. It's how do we find out what to do? And if we find out what to do, we're going to find it out by mathematical experimentation. And here we are presenting 4 different performance productivity analysis. The first one, which is without climate change. A current climate, a current hydrology, current operating rules, and a current physical system. Let's find out what this produces. And let's use optimization technologies in order that the operating rules are reasonable and they're optimal. So we now have a benchmark. Now that we move into the second phase of this, in which we say there's going to be climate change is going to take place. We have to choose one of these scenarios, one of the 90 of them, or something of this case. But it's going to have a result of a change in the hydrology. So let's reevaluate the system again. Using, in this particular case, the situation with the initial operating rules have not been changed, the initial physical changes are not being had. It's as though we were operating with blindfolds on our faces here, and we're doing things exactly like we were doing in the past. Well, climate change is going to have a detrimental impact on it. We saw that from one of the previous. We'll see this later in another slide. Well, we're still not reaching the thing. We're going to, even in this case here, with a change in climate, etc., we're evaluating a hypothetical situation. which has not been fully adapted. So let's move into the third adaptation evaluation, in which we say, now we are going to change the operating rules. We're going to change the way we operate this system. And then how are we going to find this out? Well, we're going to use mathematical simulation and optimization technologies. We're going to use the projected hydrology, the projected climate, etc. And we're going to find out how to operate if, and this is very important, this word if this climate event took place. We haven't made any physical changes. Now let's take a fourth scenario where we say, we're going to really have to do something about this. We're going to change not only the physical, the operating rules, but we're going to change also physical configuration.